My name is Dave Ekman. I'm with Magnuson Clementic Associates. I'm the moderator for this session, as well as an NASCC Planning Committee member. And this particular topic is of interest to me for quite a long time, actually since I was a recipient of a fellowship where I was traveling in Europe for an extended period of time. And I noticed that castings were very common in Europe. And as I came back to North America, I'm really, why aren't we using them here? And I think it's a great tool for structural engineers to have in their tool belt, but we need to know more about it. It's the questions of where to even start. How do I start to design something like this? What does it cost? What's its availability? Are there any welding considerations? And so what we have today to start that conversation is three eminently qualified speakers with us. And I'll apologize to them because they took the time to send me these nice bios, and they're very qualified to talk about this topic. But in the interest of time, I'm going to make them very brief introductions. We have three speakers today. Our first speaker is Raymond Monroe. And he's the Executive Vice President of the Steel Founders Society of America. SFSA is really the representative of all the foundries in the United States, similar to how AISC is representative for fabricators and erectors around the country. You're going to see when he speaks that he knows steel castings inside and out. Our next speaker is Carlos. Carlos, I always struggle with your last name. I'm going to apologize for this, but Oliveira, thank you very much. and Carlos, he's a co-founder, president, and CEO of Cast Connects. If you haven't been there yet, he's exhibiting also downstairs, so you should go check that out. But they're the largest design center and supplier of steel castings in North America. And actually, we're using some of his castings on a project that we're doing up in Milwaukee, Wisconsin right now. The third perspective that you're going to get is from a design engineer, and that's a colleague of mine named Tom Meyer. And he's a principal at Magnuson Clementic Associates. He designs many large, complex structures around the country and around the world. And one of the projects that I hope he's going to talk about a little bit today is San Ysidro border crossing, where he worked closely with Carlos and others about the use of steel castings on that project. Now, this session is a little bit different in the sense that it's, in addition to getting your learning units, it's also being recognized by the American Institute of Architects as a learning session for them as well. So maybe the first question is, do we have any architects in the room? All right. Fantastic. Well, that is great. And I will take the time to go through the protocol here of what I do need to do. I should say I was asked to read this statement that this session is part of the NASCC Architects Program State of Sessions and is approved by the American Institute of Architects Continuing Education System for the Learning Unit credits. After the conference, AISC will follow up with the Architects Program registrants to confirm their AIA number and report attendance. If you are an architect but did not register for the conference through the Architects Program and want to receive learning units for this session, contact AISC's Larry Flynn at flynn@aisc.org. Okay, Larry's in the back of the room there. Yep. So, and actually, do we have a sign-in sheet? Is that helpful? Or? All right, fantastic. And again, Larry's in the back of the room. If you have any questions, his email is flynn@aisc.org. Okay, for the engineers that are looking for their PDHs, you'll see the code number there for this afternoon's session. And again, because it is an AIS session, AIA accredited session, there are a few things that I need to talk about. And that's just to recognize that this course is registered or recognized by AIA. I talked about that. That's all I really need to talk about there. The course description, we're going to be talking about steel castings, the advantages of it, and how its applications are growing in North America. I'm not going to burden you with watching me read this, so I think you can read it yourself and just course. Pardon me? Okay. I think this is pretty typical to all the AIA sessions that you've gone to in the past, and you'll recognize the format. The other thing that I do need to mention is that there are specific AIA learning objectives here. And so the four things that we're going to talk about today that you want to be able to walk away with is certainly comparing the advantages and differences between steel castings and cast iron. There's a little bit of maybe a misperception about what the two are, so you'll learn a little bit more about that today. We're going to also, objective number 2 is evaluate how steel castings are produced and how they're delivered to project sites. We're going to also talk about identifying steel castings that explore how they are incorporated into commercial projects. And then you're going to hear a little bit about a forthcoming design guide that is still in its infancy, but between SFSA and AISC, we're trying to advance that ball so that we have a tool for engineers to learn about how to design steel castings. So with that, I'm going to hand it over to Raymond Rowe, our first speaker.
Great. Thanks, Dave. They're recording this, so I have to speak into the microphone, which really inhibits my ability to be active, but that's okay. Steel castings, I'm going to have this slide up close to the end, so if you have questions, we have a booth. You can come by and visit. That's my contact information, phone number, and email address if you want. The steel casting industry, we're really relatively small. The U.S. economy uses about 130 million tons of steel a year, and likely the largest single market segment is building construction between rebar and wide flange shapes and the other things that you use. The U.S. steel making industry only makes about 100 million tons. After 1980, they decided they'd rather work at capacity even when the market was down rather than have enough capacity for the peak. So at peak market demands, we import about 30 million tons of steel. The iron and steel casting industry makes about 13 million tons of product a year. Most of that is iron, and a lot of the iron is either ductile iron pipe for construction sites or automotive applications. The steel casting industry, we are small, we are tiny. We're 1.3 million tons. So we're about 1% of the steel making industry and about 10% of the metal casting or iron and steel casting industry. Half of what we make goes into the railroad industry and side frames, couplers, bolsters, and etc. And the other half goes into everything under the sun. Virtually all of it's custom product. Steel casting is a really relatively recent, in terms of human history, event, not in terms of our own personal lives. So you probably have the sense, because the Chinese were making brass and bronze castings 3000 BC, about 5,000 years ago, and cast iron was being made 1000 BC or 3,000 years ago. You probably have the sense that steel castings are thousands of years old. But we really didn't understand how to make steel castings. We couldn't melt steel until relatively recently. In the last 150, 200 years. Before that, you couldn't melt steel. So if you've been over to the Alamo and you went through the Bowie knife exhibit, I do blacksmithing on the side as well, and the exhibit there is technically incorrect in a number of ways. And one of the things they have is over where they have the video of the forging thing, they say that in the fire of the forge, you can get the metal up to 2,800 to 3,600 degrees Fahrenheit. That's just not correct. That'd be 2,000 degrees centigrade. If we could get a fire up to 3,000 degrees Fahrenheit, we could have melted steel for 3,000 years. It just isn't going to happen. In fact, cast iron can't be melted just in a fire, in a combustion source. So to melt cast iron, you actually had to build a chimney or a cupola or blast furnace. This is a stone furnace. And with a stone furnace, it took them about a month to get it hot enough to actually operate by putting a fire in it. And then what you would do is you'd put charcoal, iron ore, broken pieces of iron that weren't worthwhile anymore, and a little bit of limestone. and you had to have blown air in. So normally there's a creek here. This is Tannehill in Alabama. There's a creek here that runs a water mill so that you can have bellows, forced air, because you have to have forced air and charcoal because you can't have all the volatiles in the wood. And the carbon in the charcoal attacks the iron oxide. That's an exothermic reaction. And so with the forced air, you can get up to about 2,000 degrees. And with the reaction between the charcoal and the iron ore, you can get up to 2,500 degrees, which is about what you need for melting cast iron. And melted cast iron absorbs some of that carbon, so in its natural state, in an ordinary cast iron, it's about 4% carbon and about 0.5% silicon. That's what they make in a blast furnace. That's what they make in a cupola. In a cupola, they actually operate it more carefully, and so it's only 3.5% carbon and about 2% silicon. But it's high in carbon, and it's because you have to have carbon. Now, we don't use charcoal anymore. We use coke, but all coke is coal that we've made into charcoal. So we do exactly the same thing that you do to make charcoal to make coke. We take coal, we boil off all the water, we burn off all the light oils, and you end up with this porous carbon source that you use. And so the next slide I have is a friend of mine who worked on historical stuff, and this is a little 55-gallon drum cupola that they have that they work with students on. And the students made these little molds where you have a box, and then they could draw anything they wanted into the bottom of it. And when they drew what they wanted to into the bottom of it, you can actually pour that. So this is after melting the iron, and they're pouring it into a little ladle there. And then they're going to come over and pour into these open-face molds. And those open-face molds let each kid take home a little plate with whatever he wanted. And the flexibility is tremendous because that molten iron or molten steel will completely take the shape of the mold itself. Okay? And that's how we used to make castings. And so that's how cast iron is made. Cast iron now, oftentimes we remelt cast iron in an electric furnace, so we may not make it this way, but this is still a very common way to make cast iron. Charlotte Pipe makes gray iron fittings for internal building construction. And they're one of the dominant suppliers of those soil pipes that you put in high-rise buildings. And they make cast iron using a great big cupola in Charlotte, downtown Charlotte. Cast iron, because it can take the shape of the mold, can make beautiful castings, just wonderfully beautiful castings. And we're mostly familiar with cast iron cookware. If you're old enough to have worked on old engines, the engine block and the head were made out of cast iron. And if you were like me in Alabama and you didn't keep your antifreeze in your engine, if it got too cold, you could crack the block, and that was a bad deal. And the reason it would crack, the reason it's called gray iron is because this is the microstructure of gray iron. This is steel. This is actually, if you're a metallurgist, this is pearlite, this is ferrite, that's steel. And these flakes are graphite. They're pure graphite. And while it's not clear from this cross-section, the graphite is continuous and it surrounds little puddles of steel. So when you break gray cast iron and look at the fracture surface, you're looking at the graphite, which is why the fracture doesn't look bright like steel, it looks gray like graphite. That's what makes it gray cast iron. In fact, if you bury soil pipe that's gray iron in an acidic soil, it can actually completely consume all the steel, but the pipe will stay together because the graphite is continuous until you get some load on it. That's called graphitization. And one of my early failure analysis projects was the graphitization of a pipe in Auburn that broke and blew up because it was a natural gas pipeline and blew up one of the buildings there. So that's graphitization. And you can see that a class 40 gray iron, 40 used to be 40 KSI, you have a yield strength minimum of about 29 KSI. And because of this graphite continuity, you have almost no ductility. So in tension, it's not a very good material. But in compression, you've got plenty of properties. Okay? And so gray cast iron was a great building material 200 years ago. Because at that time, you had wood, if you had a tension load. You had stone if you had a compression load. And if you used gray iron in a compressive load, it was a great material. It worked very well. But that's not the way we make steel. The way you had to make steel is you had to get rid of all this carbon. So the way you did that was you put it in a little puddling furnace and you got it as hot as you could, and you couldn't get it hot enough to melt, but you could get it hot enough to burn out all the carbon and convert all the silicon to slag. So wrought iron is basically pure iron with silicon stringers in it, silica stringers, glass stringers in it. So when you go look at an old anchor and it looks like a piece of wood for the shaft, but it's rusted, that's because it's wrought iron, and it only rusts until it hits one of these glass layers and stops. And since they forge it and fold it, forge it and fold it, these are long stringers of silica, and so it looks fibrous. And so people used to think if you wanted ductility, you wanted a fibrous fraction instead of a brittle appearing fracture, and part of that came from this wrought iron. To change the wrought iron into steel, you had to put the carbon back in. So you got blood of a virgin and horse manure and wrapped it up in leather and put it in the forge for a week, and then you picked up a little bit of carbon. So it wasn't hard to make edged tools that way. In fact, people would make little ribbons of steel. So when I was young, my dad would tell me if I hit the axe into the ground and chipped the edge, I had to be careful because I could sharpen the edge away. That's because 200 years ago when you made an axe head, you made the axe head out of wrought iron, and then you welded a steel ribbon on the edge of it to hold the edge, because that's how precious steel was, how difficult it was. Now the challenge with that was it wasn't good enough steel for the coming industrial revolution. In fact, the real challenge was the information technology requirement of the most advanced weapon system in the world in 1700. In 1700, the most advanced weapon system in the world is a British man-of-war. The information that they didn't have is their longitude. Latitude was easy. You're only going 6 miles an hour. You're not changing very much. And so every night you can shoot the angle between the North Star and the horizon, and that tells you your latitude directly. But telling your longitude is a problem. And so they figured out a way to tell longitude. Basically, you got a sextant, and in the middle of the day, you had somebody look at the angle between, this is from Master and Commander, this is a sextant, you had them look at the angle between the horizon and the sun. And when the sun hit its peak, you wanted to know what time it was. But not just any time, you wanted to know what time it was in Greenwich, England. If you knew what time it was in Greenwich, England, when the sun went to its highest point, then you knew how far west you were from Greenwich. And to do that, you needed a chronometer that kept good time. A chronometer is a watch that's about a foot by about 8 inches thick. This one is in San Francisco if you get out there in the Maritime Museum. So that's how, but to make this chronometer keep time within a minute a month, you needed good springs. And those springs needed uniform carbon content so that you could have reliable mechanical properties. And so a gentleman named Huntsman in 1730 figured out how to melt steel. And that was called the crucible process. So a lot of the old steel companies called crucible steel were called crucible steel because that's how they learned to melt steel. And the way you learned to melt steel was you used the same trick we used to make cast iron, just a little bit different. You would put cast iron in this furnace and you would get it really hot. In fact, you would get a whole chamber hot and then come back and have the exhaust come out. And then you'd reverse the flow so that the air would be preheated as well as the fuel so that you could get this to around 2200 degrees instead of 1800 degrees. If you could get this to 2200 degrees, cast iron melts at 2100 degrees. So you could melt the cast iron. When you melted the cast iron, you dropped iron ore in it, which is just iron oxide. And the iron oxide, the oxygen would react with the carbon, and it would look like it was boiling. So that's what the carbon boil was, and you'd basically put enough iron oxide in, about a third of the weight of the charge of iron oxide, and the temperature would go from 2500 to 3000 degrees. The carbon content would go from 4% down to 0.2%, and you could make 2 pounds of steel in about a 12-hour session. Wasn't very efficient, but that's the way you learn to make steel. So steel has very low carbon in it and doesn't have the graphite flakes. And that's the way we started casting. So the first steel casting was made in the U.S. in 1861. But we make steel the way all the steel makers do. They make it the same way we do. This is a steel foundry in Amite, Louisiana, Amite Steel Foundry. This is been melted in an electric arc furnace, which is the way Nucor makes their steel. This steel is the scrap from the World Trade Center. It's been remelted, and they're pouring the bow stem for the USS New York. You may have seen this on the Discovery Channel. This is one of our member companies. A bow stem is a critical structural element of that battleship, and it's a steel casting. So steel castings are real steel. In fact, all the steel you ever buy is cast. Okay? You may do something with it different after you cast it. You may roll it out, you may forge it, you may do something else, but all steel starts out the same. We pull from the same scrap pile, we put it in the same kind of electric furnace, we melt it, and we pour it into some kind of mold. Now, in steel castings, we are not inexpensive sources of steel. We may be very inexpensive sources of the final component you need or the engineering requirement that you have. But we spend as much time making the shape as we do making the steel, and since we're making custom parts in small batches, we're not efficient steel makers, and we have to make your shape. So, if I want to make this valve body, this is really clever because I can make these holes in the casting itself. What I do is I make a mold out of sand, and I hold the sand together with an organic glue so that when I pour the steel in, the mold lives long enough for the steel to solidify, but then there's enough residual heat in the steel to burn all the organic glue away so I get the part. But to make this part, I not only have to have a hole in the sand that looks just like this part, I also have to have a plumbing system to get the liquid metal in. And then when steel goes from a liquid to a solid, it gets smaller, so I have to put reservoirs called risers on top of it so that it can feed that casting. So to make this casting, this is in fact the kind of structure that I would use. And that structure these are vents to let the air out of the casting. These are the risers to feed the shrinkage, and this is the plumbing system. This plumbing system actually has a filter on it to make sure that I don't get any inclusions. So you can see that this is all that terminology. We're not going to go through it. A core makes holes inside the casting. Castings are really clever because I can make any shaped hole I want to on the inside. One of the problems with manufacturing processes is there are no good ways to make inside shapes. So we may have to make two pieces and put them together to make an inside shape. In steel castings, we can't violate that rule, but we have a really clever solution. We make a sand piece with the glued sand that the outside shape is the inside shape you want, and then we pour steel around it and let it burn away. If you couldn't do that, it'd be really difficult to make internal combustion engines. That's how we make heads and blocks. It's the only way to get those complex internal passages. So this is the kind of mixer we use to make the bonded sand. We use a pattern, a tool to put the hole in the sand. Then we use a box to build the thing to make the hole down the center. Now, we really are modern, and so we can use additive manufacturing. In fact, we are the most advanced users of additive manufacturing. And so basically, this is X1 Corporation. They sell this meter by meter box. This is a printer head, and basically you put a layer of sand down and then you print the binder on it. And after you print the binder on it, then you can vacuum out all of the sand that's loose and get the mold you want so that you can make the most complex parts. So instead of now having to pay for tooling, we can make parts in a week, in 2 weeks, if you really want to pay the premium to get those prototypes. We also are some of the most advanced users of digital engineering. This is a fluid flow model of making something that looks a lot like the valve I showed you. These are the risers. That's the plumbing system. You can see the velocity and the flow pattern. That's how we make sure that we get the high quality metal laid into the casting without damaging the metal. And then this is a solidification pattern because the last place to solidify is the one that's going to have the shrinkage. So there's a little shrinkage pocket right here that may require we change the design or we do something else. So we actually have very sophisticated tools to make sure that we make sound castings and provide a high quality product. Steel castings are used in nuclear power plants, nuclear submarines, aircraft carriers. So this is steel castings. WCB is a carbon steel. It's really a 30 KSI minimum, 42 KSI typical yield strength, 25% elongation, and it's weldable with the AWS pre-qualified procedures with the engineer's approval. So you can't just use it directly, but if you have the engineer's approval, it certainly is capable of using those weld procedures. There's one other cast iron, since that's part of your requirement, and that's ductile iron. For the last 50 years, ductile iron's become more attractive. Gray iron doesn't have any ductility, and so ductile iron, if I add magnesium to that 3.5% carbon, 2% silicon, I can get the graphite, instead of being flakes, to be little BBs, little ball bearings. And so that's called nodular iron or ductile iron or spheroidal graphite iron. And ductile iron has really nice properties. It's got, because if I put 13% by volume holes in my carbon steel, I would also get 50 KSI yield strength and about 6% ductility. So that's how they get the strength. They can actually change this by heat treatment to put more carbon in or take carbon out, so they can make it stronger, but they have the trade-off. The stronger they make it, the less ductility they get. They have usable but not at fantastic fracture toughness. So any place where toughness is really a concern, or this material is really not weldable by ordinary means because you've got this 3.5% carbon that really limits you. One of our real opportunities, one of our real success stories are these unit trains that brought coal from the Wyoming Powder River Basin. They have 24,000 horsepower carrying 100 cars. The cars weigh 250,000 pounds each, or 125 tons. So there's 12,000 tons being pulled by 24,000 horsepower. And we make the couplers, the side frames and bolsters. And Bradkin, who's here, who's made a lot of these castings, actually makes the locomotive truck frames. Those locomotive truck frames have to have 2 million side fatigue resistance in order to be qualified. So as Dave mentioned, we are working with AISC to do a joint design development. We were successful at getting some Department of Defense grant money, so we got the funding to develop a design guide that should allow the castings to be fully characterized, tested, to set design allowables, NDT requirements, and pre-qualified weld procedures to facilitate your use of steel castings. We know that this is possible because if you look at the materials that are already listed, now the castings are not in the pre-qualified procedures, but these other materials are. If I look at the ASME requirements, we have the same allowable stresses for the steel castings as they do for the plates and other materials. And so this shows the welding practice, and that's my last slide, I think. So thank you for your attention, and I'll turn it over to Carlos.
Thanks for that. I am not a metallurgist. I am a structural engineer by trade. I also like to think of myself as an industrial designer, and so I hope my presentation might relate a little more to your everyday activities as structural engineers and architects. So my name is Carlos de Oliveira, and I'm the president and a co-founder of CastConnex Corporation. Our company exists to enable architects and engineers to leverage steel castings in their design. And we take a lot of pride in what we do because castings can make buildings more economical, safer, more resilient, and certainly more beautiful. And so we take a lot of pride in what we do, and we take a lot of pride in enabling architects and engineers to use steel castings. Just so that you don't get the sense that castings in buildings and bridges are new. This is a map showing all of our projects in North America. Many of those dots have overlapping dots, so we have put over 10,000 steel castings into service into buildings and bridges all over North America. As Raymond said, all steel is cast. And so what you're looking at here, this is a continuous casting process at the far end that's producing hot-rolled wide-flange sections. The difference with steel castings, though, rather than hot-rolled sections, is we pour molten steel into complex-shaped molds. And the molten steel can therefore take the shape of that mold. But what does that mean to us as architects and engineers? Well, castings make geometries, but we make buildings and bridges. And so it's incumbent upon us to understand how we can leverage that free-form geometry to improve the structural performance or architectural performance of our buildings. So here you see a cast node that's used in an offshore wind turbine basement structure. And the purpose for this connection is to improve the fatigue performance of the overall structure. So as you're looking at this cast node, you can appreciate that you can't make a monolithic structural steel component of that geometry using any other manufacturing technique but steel castings. I can't roll and bend and weld plate work to make that geometry. But it's not just a geometry and it's not just a shape. This node in this structure makes that the total life cycle of that structure 10 times longer. So that connection can resist 10 times the number of cycles than a conventionally fabricated connection would otherwise be able to carry. Now, when I look at that connection, I also think it's very elegant, it's very sexy. It would make a really nice architecturally exposed connection feature for my building. But suffice it to say, this is a cast node for a wind turbine that's going to be installed in the North Shore. In the North Sea. And so the fact that it's very elegant and beautiful looking is completely irrelevant. And really the use of castings in this structure, as I said, are increasing the fatigue performance of this structure and this connection, and therefore making the total structure much less costly. And the way that cast nodes work in that sense is actually very simple. If you think of a conventional weld fabricated connection, we put the weld really in the worst possible place we could think of. It's right where the geometry is complex, right where your forces are highest, right where your stresses are expected to bend the corner. So you can see in, say, for example, a tube-to-tube welded connection, that welded joint has got a very high stress concentration just by virtue of the geometry of that connection. But it also has a high stress concentration factor because welds inherently have defects in them. And so if I look at the stress concentration going through that connection, I get a very high spike at that welded joint. And so if I load that connection in a fatigue type regime, after a certain number of cycles, that connection will fail at that welded joint. Someone in the late 1970s, early 1980s, thought of using castings to address this issue in very complex structures. And the idea was if you replace that junction with a monolithic cast node, you can use the casting process to put the material where it ought to be for the flow of forces through that connection. So I could make that a very smooth and generous radius to reduce the stress concentrations through that geometry. And then I move the welded joint away and separate it from the geometric stress concentration. And so by doing so, we can significantly reduce the stresses in that welded joint and significantly improve the fatigue performance in that connection. And we can, as I said, we can improve the fatigue performance of those connections by an order of magnitude, a factor of 10, and that means that structure will last 10 times longer. So we often get the question, how do castings cost in comparison to fabricated connections? And it's kind of a silly question when you think of a structure with castings will last 10 times longer than a structure that's just weld fabricated. So unless the weld fabricated structure is 10 times less costly than the structure with castings, then we shouldn't even be having that conversation. So as I said, the history of casting use in structural engineering started in the late 1970s, early 1980s in the offshore oil industry, making connections to address these fatigue criteria. This is a very large offshore structure. Just to give you a sense there's some cars on that island. So this is a very large structure that would then get floated out to sea. And this is what one of those cast nodes in a structure like that might look like. And again, you can appreciate that you can't really fabricate steel to do that. We're making that geometry with castings. And again, I look at that and I see design elegance. I see potential for architecturally exposed structural steel. But of course, this casting is being used to address those very arduous fatigue demands in those structures. On the right there, you see a section cut through that node, and you can see how we can put the material where it ought to be for the flow of forces through that junction. So you can see how the wall sections taper in size to reduce the stresses at those complex joints, and how we move the welded joints away from that geometry and therefore improve the performance of the structures. Another advantage to using cast steel nodes in, say, tubular connections is that they can address all of the local connection limit states. So if I'm a structural engineer and I'm designing an HSS truss, for example, and I have local connection limit states that I have to concern myself with, like cord wall plastification, for example, those local connection limit states might ultimately drive the wall thickness requirements for all of the tubular sections in that structure. So the whole structure has to be heavier just to address local connection limit states. Whereas if I replace that junction with a cast node, all of the tubular members framing into that node can now be thinner walled. And so therefore the use of castings can actually reduce the overall tonnage of complex tubular structures. And so the first onshore structures to start to use castings in a big way was in Europe in the late 1980s, early 1990s, and we saw it used predominantly in highway bridges and in other fatigue-critical structures. And there in the inset on the bottom right, you can see that cast node, how all of the geometry of that junction is dealt with in the casting. Look at the wall thickness in that casting. And you can appreciate how all of those connection limit states are being addressed, and now the tubes framing into that casting could be much thinner walled than otherwise would have been possible. Again, here aesthetics are not playing a big part in the option or the decision to use castings, because the viewing distances are very far. A pedestrian walking by underneath that highway bridge wouldn't really appreciate that that's a cast node rather than a weld fabricated connection. But again, the use of castings is reducing the tonnage in that structure, and it's improving the fatigue performance of that highway bridge. But it didn't take long from there, really, once castings started being used in onshore structures, for architects to really grab on to castings and to start to play with the possibilities from a geometric perspective. And so here, for example, is the Stuttgart Airport, which was constructed in the early 1990s, which featured tree-like structures that support a roof. Now, you can appreciate this is not a fatigue-critical structure. This is just, it's a building structure. It's just these trees are supporting the roof over top of this terminal. But you can appreciate how the cast nodes in this tree, the castings are being used to kind of become part of the aesthetic, to sell this tree more like an organic tree structure. You might be able to address that joint with fabrication by bird mouth cutting the pipes and bringing it all together and using internal stiffeners to address the forces, but you certainly couldn't make that connection look like this with anything but a steel casting. And so in this case, again, the casting is addressing complex geometry. It's improving field welding access. So you can imagine if you were erecting this structure, you would have shop welded that node to the lower column and maybe had to field weld some of those upper branch members to that node. But because it's a cast node, you have good weld access all the way around. Those are just now circumferential welds rather than complex TYKs on, say, a complex bird mouth connection. And so we're addressing all of that geometry, we're simplifying field construction, but also it's a big part of the aesthetic and a big part of the architecture of that space. And as I said, with steel castings, we could put the material where it ought to be for the flow of forces through the junctions, or we could throw that out the window and then just create purely creative design details and connection details like this one. These are timber columns sitting on top of steel castings, and so obviously timber not being capable of carrying the type of loading that steel is, we don't need much steel material, so we can pull it away from there. But a big part of that shape is the aesthetics. It's interesting to see, having been in this space, how the connection details actually affect the architectural quality of this space. You can see children are just immediately drawn to these things. You know, they're putting their arms through it and trying to climb through, and they're interacting with the structure of this building in a way that is very different from anything that I've seen before. And as a designer, I think that it's very interesting to think about how connection details and design decisions like that can actually really impact the architectural quality of spaces. So when we're thinking about using steel castings, we're often thinking about our clients' money and not wanting to spend it frivolously. So the best way to do that is to use castings when they make most sense, and that is architecturally exposed structural steel connections. Connections, particularly for hollow sections, as you saw, a lot of the examples I showed are for hollow steel sections. If you're mating different materials together, you can leverage castings to address all of the various connection details, whether welded, bolted, or otherwise tensioned together. Complex connections, arduously loaded connections, connections that would require a lot of stiffening, particularly if the stiffening is internal. We could easily make the castings wall thickness increased to address those stiffness requirements. Functional applications to simplify fabrication or speed erection. So by using and leveraging casting geometry to, say, for example, provide a field bolted connection rather than a field welded connection, we can create a lot of value and build a lot of value into these cast steel geometries, and make it really impossible to value engineer these components out of projects because they just provide so much value to their projects. And of course, fatigue critical connections, but unless you're doing bridge design, that's probably not a big part of what you're looking at. So the best applications for steel castings are ones that hit on as many of these as possible, ideally all of them, but even just one could make the castings from an economical perspective make sense. So I'm going to show a number of projects that have used steel castings in North America, just to give you a sense of what's possible. The Queen Richmond Centre in Toronto is one of our marquee projects, just because of its kind of structural ambition. Here we have an 11-story reinforced concrete office tower that's perched entirely up on stilts above two existing heritage structures. So here you can see in yellow are the architecturally exposed structural steel stilt structures. They were called delta frames. They're 70 feet tall. Each of the tubular members is 40 inches in diameter, 2-inch wall thickness, and had to be concrete filled just for the loading coming from the gravity forces from the tower above. And of course, because of the arrangement of these frames, they also participate in the lateral force resisting system of the tower above. The design calling for these 70-foot tall towers and perching the building up on top of these towers created a very interesting atrium space. And so that was a big part of the selling feature of this architecture to the client, was that they were going to create this soaring atrium space that was going to be a part of this commercial development. At the time when we became involved in the project, the design team didn't really understand how they were going to address that complex connection at the center of each one of these frames. You had 8 tubular elements all coming together, extremely heavily loaded. And so they started talking not only with ourselves, but also with steel fabricators. The steel fabricators in Toronto came up with this idea. They would introduce an 8 or 10-inch thick steel plate and move the legs out from one another so that they could do circumferential welds, and they might kind of fabricate a node and then bring the tubular members into that fabricated node in the field. But this had a lot of challenges. As I said, the legs of this tower had to be concrete filled, so they weren't sure how they were going to get the concrete through that center plate. Also, I mentioned that the towers participate in the lateral force resisting system of the tower above, so when the wind blows on the tower above, the whole delta frame wants to sway. And so all of that shear force has to go through that single plate that they were talking about putting in the middle. And so they weren't sure even if that plate was going to be sufficient, or how they might even analyze or design that kind of a connection. Simultaneously, ourselves as a casting designer and supplier were looking at the problem, and we developed a cast node solution, which was a cast node that was cellular in design, so you could pump concrete from the bottom of the leg all the way up through the cast node, 70 feet up into the air from all 4 sides, addressed all of the structural loading from the building above. I believe it was 100 meganewtons of force, which is 20 million kips, I believe, of force down on top of the cast node. And and also, and perhaps most importantly, addressed the architect's desire to create a monolithic-looking structural element. They wanted this element to look as if it was one piece of steel. And obviously, this is a very important aspect of this space. You walk into the space today, and you almost forget that these structures are holding up a building above your head. They just look like sculpture. It's just beautiful. And here's a picture of that cast node, which weighed about 35,000 pounds. And here you can see and get an appreciation for just the strength of steel castings and the way that we can very readily address all of the forces in a connection like that. You could see the cast node at the center of that delta frame. And here in the finished condition, you can see how that structural form is really monolithic in its appearance. It reads like its vertical swooping legs that just seem to kiss each other at the center of that delta frame. And it makes it look effortless almost to address those forces. Another project at the University of Connecticut, it's currently under construction right now, the Innovation Partnership Building. Here, the designers opted to perch a portion of the structure on top of V columns underneath. You can see there circled are the V columns. And at the time that we got the call, the designers had some interesting ideas about those V columns. They were going to fill them with concrete. They had some really complicated pin-type connections that required shear keys and embedments into the tubular elements with all sorts of shear studs to try and engage the concrete filling of the tubes. They had a fabricated connection at the base of the V column, which they were going to then clad over top of with some architectural covering, so you wouldn't actually see the pin connection at the bottom. And so when we approached this, we kind of started carte blanche and said, well, can we not just eliminate that concrete altogether? And in so doing, we did come up with a solution, a steel-only solution that eliminated the need to concrete fill those elements. But the savings that provided actually ended up paying for steel castings for the project. And so we were able to convert those top fabricated connections into standardized cast steel components. And also the V-column base we converted into custom casting. And so here you can see, these were 24-inch diameter sections. So here you can see the clevis type connection on the left, which is actually a standardized off-the-shelf product. And on the right, a custom V-column base for the base of that V-column. And here you can see that put together. Note that you can't see where the casting starts and stops. Again, this is a monolithic form. Neither the bottom nor the top casting, everything is really uniform and really elegant looking. Charlotte Douglas International Airport is another project that is currently under construction. In this case, we had a 140-foot long roof truss. The trusses were about 30 or 40 feet on centers, and so very large span coming down on, again, V columns. And at the base of these V columns, not only do you have to support the weight of all of this structure above, but you've got these connections that also have to be blast resistant and fire resistant and also are exposed to view at very close range. And so the designers wanted to do something special at those connections. There at the bottoms there you can see circled in red. Some of the design considerations for the use of castings here: significant gravity and lateral load, wind and seismic. Basically, these castings are supporting the entire structure. Blast loading considerations, as I said, fire resistance, constructability. We had to think about how these connections would actually be constructed, for what was going to be done in the shop versus what would be done in the field. And again, exposed to view at very close range. In particular, the architect was quite concerned about the use of intumescent coatings on top of the connections, especially if we're going to have articulated cast features at the base of these columns. They were quite concerned about how that might look with kind of intumescent coating that I've heard been likened to cottage cheese just slopped on top of the architecturally exposed structural steel. And so we came up with a very elegant solution, I think, where we actually express the casting as a separate element from the tubular steel that frames into it. So the columns above the cast node, which are hollow steel sections, are intumescent coated, and the intumescent coating actually ends at the cast node, and then the cast node is going to be coated in a different colored high-performance coating. To address the fire and blast resistance, we designed the casting so that it could be concrete filled. And so you see on the right a section cut through the casting showing that the concrete filling. And here you can see just a close-up of that joint detail as to where the two types of coating systems are going to transition. You can see the wall of the hollow section, the partial joint penetration weld, all being covered with intumescent coating, and then a purposeful reveal being cut into the casting to emphasize the difference between the pipe and the cast node. From a structural analysis and design perspective, ourselves as casting designers, we conduct complex finite element analysis, and that's because castings are non-prismatic complex geometries. They're disturbed region bodies. Beam theory does not apply. You can't just use beam theory to determine the forces in these elements. They're disturbed regions or D-region elements, and so you typically need finite element analysis to determine the stresses in the casting. Once we understand the stresses in the castings, then we'll set non-destructive examination criteria for the manufacturing process. So that will tell the manufacturers of the castings what is the largest indication that we can accept at the various regions of the casting. And in the event that any of those regions show an indication that's larger than our criteria, that area would be weld repaired in process prior to the final stress relief. So at the end of the day, we have a monolithic cast steel component that simultaneously meets our quality criteria and is capable of resisting the forces that are applied to it. For this particular project, we had 32 cast nodes. So at each one of those locations, there's a different set of loading that's applied to it. So ultimately, we had 1,044 FE cases to run and analyze and to consider all of the stresses that were in that joint. And of course, you can't run the finite element analysis until the full geometry of the casting has been determined. And most structural engineers don't have that capability to fully define the geometry of a casting. So that's one of the reasons why that we are a big proponent of delegating the design responsibility to the casting supplier, because we'll see the contract documents, we'll see the forces on the cast nodes and the extent of the cast node. We understand what you want from a geometry perspective, and then we design it so that it's capable of carrying those forces, and we set and establish all of the non-destructive examination criteria. So here you can see that casting completed. Again, you can see that reveal that was machined in, which is another thing that we do and consider. We consider what features are going to be as cast features versus others that will be machined. So we could have cast those pockets. We could have made those as cast features, but had we done that, the edges of those pockets would have had to have very generous radii so that we wouldn't lose them in the casting process. But because they were a critical part of the aesthetics, we wanted those to have sharp corners. So we opted to machine all of those counterbores that you see in the base, and it creates a very clean-looking aesthetic. And these are the kind of the design decisions that we are making to ensure that the finished product not only is constructible and manufacturable, but actually meets the architectural intent. Another major project is the Transbay Transit Center in San Francisco. This is a project that wears its seismic force resisting system on its outside. So wrapping the entire perimeter of this structure is an architecturally exposed structural steel frame that is also the seismic force resisting system. It's an eccentric brace frame configuration where each one of the junctions in these AESS steel trees are castings. And the idea is that each one of the trees would remain predominantly elastic in an earthquake, and they'd rock relative to one another, and the shear link in between the trees would yield and shear and absorb the input energy. Just to give you a sense of scale and size of this project, it's 4.5 city blocks long of repeated framing. The smallest cast nodes on the project are there in the top right-hand corner. I'm standing beside them. Granted, I'm not a very tall person, but these are very big connections to be the smallest castings on that project. And a variety of geometries and configurations and shapes. Here you can see some of that framing coming together in the field. We consider viewing distances when we're specifying surface finish requirements for castings. So you can see that some of those cast nodes are only going to be viewed through a perforated aluminum awning, for example, whereas say the cast nodes at the base of that tree would be viewed at very close range. And so we would set different surface finish requirements for the various castings viewed at different distances. Slicing through the center of the Transbay Transit Center is a 150-foot tall steel oculus-type structure that is designed to allow light to shine into the very bottom level of this structure. That 150-foot tall structure is comprised entirely of cast steel nodes and steel pipes. And again, you can see on the outside of these castings, they don't look all that geometrically complex, but you can look at the inside and see how we've shaped those parts to address the local connection limit states, and therefore appreciate then how the tubes between each one of those castings can now be much thinner walled than otherwise possible. And here you can see how that's come together in the field. So for the Transbay Transit Center, there was 304 castings in total. I mentioned that they ranged in weight from 5,000 to 50,000 pounds each. The small ones I was standing beside were 5,000 pounds. The preliminary costing before the casting designer was engaged on this project, they estimated the cost of the castings would be about $22 million. This is a $4 billion development, by the way. So $22 million sounds like a lot, but it's not a lot when you consider the project is $4 billion. At the 95% CD stage, a casting designer was engaged. They redesigned all of the castings. We added more castings to the project, in fact, and ultimately we added 15 geometries, 46 additional castings to this project, and ultimately through that redesign effort, we saved 30% of the costs. So at the end of the day, we bought more castings for $15.5 million rather than $22 million. So that's the difference between a casting that is designed for the casting manufacturing process rather than just as a shape or as a geometry. So how, if I'm a designer, how in the world do I specify a custom casting? The answer is it's actually a lot more simple than you might guess. First, you ought to speak with a casting designer that's knowledgeable in casting, design, and building construction. Casting designers like ourselves, we have a lot to offer. We can participate in your schematic design, help you with value engineering ideas and thoughts, and enable you to specify the castings correctly in your contract documents. Ultimately, then, in your contract documents, you want to call out that certain junctions are going to be castings. You want to identify which junctions will be castings, and ideally, you want to identify the general extents. So the out-and-out dimensions, and if there's any specific shaping that you require for a structural perspective or an architectural perspective, if there's certain features that you want cast into the part, you need to show that in your contract documents. We're certainly not expecting you to size and dimension every single piece of geometry on these castings. That requires complex 3D modeling, as I said, complex finite element analysis. Ultimately, it will need computational fluid dynamics and solidification analysis, but all of that is going to happen after the fact. So you just need to set the ultimate general geometry and out-and-out dimensions of that casting. And then you need to create a performance specification, and this is possibly the most important part. In your performance specification, you need to delegate the structural design and the final design of the castings. You need to require certain submittals like shop drawings. On your drawings or in that specification, you need to identify what loads the casting is intended to resist. And once we have all of that information, a casting designer like ourselves has enough information to then bid on that project when it goes to tender and to ultimately engineer, design, and supply those castings to the fabricator on the project. Everything I've spoken to up to this point is about custom designed castings, but there are a plethora of standardized castings available on the market that can be used in everyday structures, you know, not just maybe transit centers and stadiums and crazy commercial projects like you just saw, but castings are used in every project. We've put castings in every type of project across the United States, from residential to research and education structures. And we do that with standardized castings. So these are off-the-shelf standardized components that can be very readily welded to structural steel sections. Here you see an example of those, like the pin connectors here that would be used at the ends of a tension or compression member. These can be used at the tops and bottoms of columns, at the ends of bracing, in web members and trusses, for example. And these are, as I said, available off the shelf in a range of sizes that fit all of the standard HSS sizes that are available. Here, for example, that those castings have been used in the Whitney Museum of American Art in New York City. In these diagonal bracing, you can see the connectors at the ends of those diagonal bracing in that structure. And when you look close up, not only do you see the cast connection that's at the end of the diagonal brace, you also see other castings, cable castings. You might not have realized, but those cables, whenever you specify a cable system, the clevises for those cable systems are also castings. So the same product, standardized, that was specified by Renzo Piano, here you can see it used at the bottoms of these columns, supporting a roof overhang in a library in Ontario. So very accessible technology that can be used on any project. In this case, for these particular pin connections, the impetus is obviously aesthetic. They look a lot better than you could probably fabricate a pin connection. But in addition, there's savings. There's fabrication speed and economy that is provided. So on the left, you see maybe what you might fabricate for a true pin type connection that you're trying to make aesthetic. And you can see that connection for a 6 5/8 inch pipe would require 102 linear inches of weld and grinding, whereas if I'm just welding a clevis onto the end of a pipe section, it's just a circumferential weld. So there's about a third of the weld to deposit, a third of the weld to grind smooth. So it's much faster for your fabricator to be able to process that steel. So there's a speed and economy there that is available through the use of these types of standardized connections. Here you can see how a fabricator might do that. They might put that tube section on a turning spindle and use an automated welding machine to just deposit that weld as the tube and casting spins underneath. And you can appreciate then that fabricator can process that high-end architecturally exposed structural steel very quickly. That's not usually the case for AESS. It usually takes fabricators a lot of time to do AESS well. But that's not the case with standardized castings. And as I said, there's lots of geometries that are available. There's, say, for example, also tapers, kind of reducers that can be used at the ends, tops and bottoms of a column. You'd be surprised how just tapering the ends of a column can make the whole section look so much more slender. So a compression element that's driven by buckling, you might need a large diameter, but ultimately the connection forces are low. So at the ends, if you taper down and have a smaller section, you can make that whole column look that much more slender. These castings, of course, can be used together. You could stack castings together and weld them. We're still talking about steel, so you can weld steel to steel. And here you can see two of those castings used together at the bottoms of these columns, for example, at this project in Worcester, I think. Here you can see a similar castings used at the ends of compression struts, again, holding a roof overhang. Very simple, elegant, light-looking, architecturally exposed structural steel that's enabled through the use of castings. Same two castings used at the ends of these rather heavy-looking, to be honest, stair supports. And here you can see the same castings used at the tops and bottoms of columns that support a canopy or timber. And talking about timber, there's standardized castings that mate with timber. And so here you can see some castings that are used at the ends of these compression struts in this very elegant looking truss. So the compression members in this structure are timber fitted with castings, and the steel members are basically taking the tension. And standardized castings, because they're standardized, all of the dimensions are known, all of the properties are known. It's very straightforward to specify them. Ultimately, you just want to speak with the manufacturer, get any cut sheets and information you need, and call out the castings on the structural drawings and in the architectural set, and include the product manufacturer specifications in your contract documents. And it's that simple. So with that, I'll pass it on to Tom here.
So thank you, Carlos, and he was nice enough to set the presentation up for me. So what I'm going to demonstrate to you today through a case study is a confirmation of how easy it is to incorporate custom or product-specific steel castings into your projects. And the project I'll use as an example is the San Isidro border crossing primary inspection canopy that was recently completed about 3 or 4 years ago and is now in operation today. So this is the canopy, and it's a cable-stayed canopy structure. And until I started working on this presentation, I always thought of that canopy as just a cable-stayed structure. But now, after putting this presentation together, I'm realizing that this is more so a casting structure, because there are custom castings, 6, but there are hundreds of product-specific manufacturer castings on this project. And I'm going to show you how we incorporated them through our contract documents and through the specifications. So as Carlos mentioned later in his presentation, the cable end fittings, each themselves, are cast steel products. So on the end of each end of this cable, we have 2 different types of castings. We have the open spelter socket on the left-hand side of the image, and on the right-hand side, we have the conical socket. And sometimes you put them together so you can have different types of adjustability on the cable. So this particular cable has a conical socket as well as an open spelter socket, and they're connected rather than welding together. They're connected by threaded rods. So the insides of the castings are internally threaded, and there's a threaded rod with reverse threads so that the socket can be adjusted. And then this is an open bridge socket, and the head block there that's used to resist the stressing jack is a cast steel element, as well as the closed spelter sockets on each side of the gusset plate. And so from the contract documents perspective, Carlos was spot on. We take the manufacturer data and we set up language in the contract documents. So when we call something an open spelter socket or a conical socket, we refer specifically to the manufacturer's product, in this case the PV800, which is Pfeiffer's conical socket. For the open spelter socket, they also have a type, and we've defined the language in our documents, as well as a threaded rod, not a steel casting per se in the context that we're discussing them today, but it is another part of the assembly. And so when you put that into the drawing detail, it's as simple as identifying which elements go together: the conical socket, the threaded rod, and then the open spelter socket. So that's what creates this adjustable cable fitting on the top side of the canopy. And then on the bottom side, we have just an open spelter socket, so there's no adjustability in this connection, but again, another casting. And so what I really want to talk about is the custom steel casting and the process we went through, first to identify do we need one or why we would need one, and then how we went about getting it successfully implemented into the project. And so the steps we kind of went through are the steps you might go through in any design process. You have a concept design, you have to do some concept vetting, you want to get the contractor involved and get the buy-in with the contractor. And then we need to think about what are we going to put in our drawings and in our specifications, and what are we going to require in our submittals. So why would we use a steel casting in the first place? So the custom casting occurs here at the node. This node has a large diameter, about a 5-inch diameter cable here, and then a node that separates it into 4 cables that resist that tension in 4 different trajectories. So we have 5 elements coming together, and you can see the different trajectories as you look at the elevation of the mast from each side. So as an engineer, after we've run our analysis model, maybe we've done this by hand if we're really good, we come up with our force vectors, and that's all we really have after the analysis. So I went into the AISC manual, but I didn't find a standard connection for this one. So I had to come up with something. Shoot. So we tried the typical, I guess, the conventional methods of connecting the cable, which is gusset plates and the open spelter sockets. And this, we talked to Pfeiffer about it for a long time, and this was kind of their stab at it. And this was mine. And I think we all agreed, and I think you would all agree, that none of those are very elegant looking. And I'm not sure those really work from a load flow perspective. I mean, this one is too idealized. Our geometry is not orthogonal like this. And I think this one's just clunky. And I don't think we really would have got the forces transferred through there at all. So I think this flew like the proverbial lead balloon. So we were kind of back to square one. So in our office, we have a rule. A 5-minute rule. If we've thought about something for more than 5 minutes, we need to get out of our chair and go ask somebody, Well, in this case, obviously nobody in our office had designed a connection like that. So what I tend to do is flip through pictures of architecture that's out in the world and try to draw inspiration from that. And so I happen to stumble across this picture, and whether Carlos sent it to me or somebody sent it to me, I can't remember exactly where I found it. But I looked at this and it sort of clicked in my head that if you turn that upside down, that's what we have. We have the large cable on the top, and then we have the 4 cables coming off on the bottom. And so this is obviously a cast steel node, and so that's where the idea of using a custom steel casting for this node really was born, was just sort of doing research or looking on the internet, trying to draw inspiration from what's out there already. And you can see the loads in this. As you would do with a cable structure, these are in kilonewtons, by the way, because this is a government job, so we had to use the metric system. But the forces are huge, so 2,500 kips in the first, and that's what it takes to resist that. So now that we've got this as a concept, we have to figure out how we would put it together. So we have the cable, and we have the conical socket in this case, and the threaded rod. And so the idea is the cable replaces the HSS, and the conical socket is what we use to thread, the threaded rod is what we use to connect the conical socket on the end of the cable to an internally threaded end of the custom steel casting. And really that's the first concept sketch of this particular connection. So we have a concept that we like. We like it from a load perspective. We like it from an aesthetic perspective. Now we need to go through the vetting process. So on a design side, we want to say, is it designable? We want to understand if it's constructible, and then we want to understand if it's going to be within our schedule. Can we get it within our schedule, and it will be within the project budget, or can the project budget consider this early enough in the process? And so that's where we engaged experts, as Carlos mentioned. The advice is talk to casting experts. And we did, and we passed load information, we passed geometry information, and we were able to get back concept level 3-dimensional images of what this casting might actually look like. So we feel like we're on the right track here. So the next step is now we've got to get the whole team on board. And so we start talking to contractor about the process. This is what we think you're going to have to go through in order to get the custom steel casting incorporated in the project. So let's talk about how you're going to procure it. Let's talk about what the lead times are. There's a bid and award time. There's a design time. There's a submittal and approval time. There's the time to actually make it. And then in the case of this one, these were made overseas, so there's time to actually get these shipped to the project site in time to get it erected. And all of that needs to be discussed as early as possible so that this one element doesn't become what delays the project schedule. It might be the critical path item, but to identify that, the earlier you can plan for that in the whole process. And that's why you have to ask yourself, is the schedule appropriate? Will we get this thing to the site on time? And so as Carlos mentioned, so far we're doing pretty good with his rules. So we've talked to them first. We've talked to the contractor, get them on board. And we chose to use a delegated design approach. So normally you might think we make this the GC's problem. Well, that's not really the case. What we see this as the engineer of record's role in all of this is to facilitate getting this special element implemented into the structure to make sure that it meets our performance requirements from a load perspective. Does it meet the architectural requirements from an aesthetic perspective? And then writing the performance specification and the contract documents in a way that we get what we want. And so this is a blow-up of the detail that we used on our drawings. And as you can see, there's not a lot of information that we really needed to provide in the documents. We provide the general design intent. It looks just like the image I showed you earlier. We provided the load case, which was one governing load case, which is based on, this is what I was trying to say before, but lost my train of thought. It's based on the breaking strength of this cable and then the equilibrium, the subsequent equilibrium of that. So the cable structure, the connection is never the weak link in the cable structure. You always have the connection capacity protected, if you will. And then we just had some simple notes about this being, the general design intent. And then the only dimensional requirement that we had was that the outside diameter of the casting as it mated with the conical socket was that the two matched, so that you could see a smooth transition from one of these elements to the other. So that's really it. We had a few items in our general notes alerting the code official that this might be a deferred submittal, and then maybe putting some material specification in the general notes. So the drawing part of it is the easy part, I would say. Then the specification is the one that you want to spend the most amount of time thinking about. And the types of things you want to think about in the specification, number one, the quality assurance section. So you want to talk about in that spec what type of relevant experience is going to give you the peace of mind that you want in terms of designing, not just creating the casting, but also in the design of it. You want to make sure that you've written a specification that meets your needs and provides a comfort level to you as the EOR as well as to the owner, the ultimate client in the project. You want to talk about the non-destructive testing protocols that you want to go through. And there would be non-destructive testing by the foundry, and then there would also be the third-party non-destructive testing. Again, similar to the processes that go on in our fabrication shops for fabricated steel. And some of the testing that you might think about are radiographic testing, ultrasonic testing, magnetic particle testing, as well as visual inspection. And this is another one that when you're delegating the design, you may want to have conversations with the designer of the casting about what are the acceptance criteria and what are the specific tests that you want to have written into the specification. You certainly don't want this to be you alone as the EOR. You have to have what you're comfortable with as the EOR in that specification, but there also may be different tests that the casting designer might want to have done based on the design of the casting itself. And there might even be some tensile testing that you take of portions of the steel. Then you want to talk about the finish. As Carlos mentioned, this is kind of what it looks like when it comes out of the process. And this happened to be, I happened to be able to be in Germany right after ours were produced. And right after that, they bring this outdoors, and it was probably a 95-degree day in Germany, and those things were kicking out some heat. I mean, you stood next to it, and it would make you sweat. So it was really kind of a neat process, which I can't actually believe they let us get that close to it, considering how hot it was, but they did. So that was really cool. So that's what it looks like. So then it goes through a bunch of surface treatment processes, and ultimately we had our castings on this project because they're exterior environment. We had them galvanized, so that occurred before they were shipped to the site. And then finally, they were field painted with a high-performance paint. Some other submittal requirements that you want to think about are the shop drawings, of course. You want to make sure that you're getting the dimensional control that you want. You may want to also ask for three-dimensional renderings. I mean, this is useful that if you want to do some type of early visual inspection of the finished geometry, this allows the architect or the engineer to spin it around and look at it and make sure before it goes into production that this is going to meet the design intent. And then as Carlos mentioned, the calculations for these types of castings are very, very detailed. And so you want to make sure that you are requiring submittal of the design report includes both the calculations and the finite element analysis results, enough so that you can feel comfortable and the designer of the casting designer of the casting has done an adequate job. And then, of course, you want to ask for the non-destructive test reports so you can see that A, they were actually done, and B, that they met the quality assurance levels that you set. And so we'll end real quickly with a quiz. And this is a little bit of a Where's Waldo, because some of these are hard to find, but the question is, can you count the castings that are in this picture? And so we have one open spelter socket here. We have another open spelter socket here. We have 4 castings here, 2 conical sockets and 2 open spelter sockets. And then hidden in the scaffolding there that you can't see, we have another 2, another conical socket, and another open spelter socket. Here we have 6, so we have the 5 conical sockets and then the 1 custom steel casting. So if you guessed 14, you get a gold star. So, and that's the end of it. Any questions for any of us?
Yeah, well, first of all, let's have a round of applause for all 3 speakers here. Appreciate that. So while I know Carlos's group has done a bunch of castings, I think as the industry, we're still in our infancy here, so there's a lot to grow on. I'm hoping this room is completely packed and we redo something like this in a few years from now. But this is a great opportunity to ask questions from 3 really experienced resources. So maybe if you guys come up on stage too. Are there any questions?
What are the surface finishing techniques that you use? Like, so for the smoothest possible casting, could you describe what's involved in?
Sure. So the question was about surface finish and how we achieve it. Well, I guess the first and foremost is that there's a range of surface finishes that can be specified for castings. The most industrial type process is something you would specify that's just called MSS SP55, and that's a visual examination criteria that ensures that the casting is the surface of the casting has integrity. It would result in a casting that looks like a fire hydrant. So you might only specify that for castings that would be viewed at a very far line of sight or very far viewing distance. So if we were doing castings that were going to be, say, for example, in a stadium roof, and they would be viewed from very far, we might specify MSS as P55, and that's a very simple kind of surface finishing. The next level up would be you can invoke ASTM standards. So the ASTM standard A802, you can specify different levels of criteria, numbers system from say 1 to 5, and the way that works is there are visual tactile reference comparator plates that form the reference against which the cast surface is compared. So if I say allow for a level 3 finish, there's a certain set of plates that then you would use to compare against the surface finish of that casting. Level 1 is the highest that is available from that specification. It would be suitable for castings that were to view in closer distance, but you're probably not going to get a completely seamless transition between the cast node and the rolled steel that's welded to it. Again, that's a process that could happen completely inside the foundry. Anything beyond the ASTM standards, that's a post-casting process. That has to happen outside of the foundry. And so oftentimes when we're designing castings that are going to be used and viewed at very close ranges, we would set much higher standards than the ASTM standards, and that is something that we would send out to surface finishing companies that would use abrasive grinding and blasting, or some actually sequence of grinding and blasting and grinding and blasting to upgrade the surface. We can do anything from a surface roughness of even as smooth as 100 RMS with a fairly standard process of blasting and grinding, or we can buff it to a complete shine. So we can make a steel casting that has a mirror finish. Again, though, as you can appreciate, that all of these different criteria and levels that we set, or all of the different surface finishes that are available, obviously have different cost implications to it. So you really want to specify the correct surface finish based on the coating system, the viewing distance. For example, it wouldn't make sense to do a mirror finished casting that's going to be coated in intumescent, right? So you have to think about viewing distance and coating, the coating system as well when you're specifying these criteria.
What's the grain flow orientation with casting? How does the grain flow work? Is it controlled at all from the design stage?
Metallurgist.
The what?
Grain flow. The grain flow orientation.
steel castings are all heat treated, and they're typically austenitized more than one time. So we get equiax grains, and so we get the same properties in every direction. And so unlike a rolled product, when you roll a product out, it always remembers the sulfides and oxide inclusions in it, and you turn them into pancakes in the rolling direction, which means if you test them in the rolling direction, you get really good ductility and properties. When you go across, you really don't, because you're squeezing them in on the side too, you don't get quite as good of properties in that direction, and the through thickness, you're looking at the pancake. And so if you're talking about the directionality, that's really what typically you get from the forging or rolling operation, not really a grain flow itself. Now, the big benefit of rolled and forged products is in the casting, the triple points of the grains, when they solidify, you'll get a little micro porosity. And so if you use a really high strength material with limited ductility, then the second phase particles really limit your ductility and toughness. But in the common materials you're using, where you've got 20 or 30% ductility, there's really very little difference between the as heat-treated properties between the cast and the rolled material. Typically, when we take in a cast material and rolled it, the properties in the rolling direction have higher ductility and toughness, and across the rolling direction have poorer ductility and toughness. The other thing you get is some grain refinement. So if you're really into advanced high-strength steels, you can get some grain refinement and rolling with thermal mechanical processing that we can't do with steel castings. We're working with the Army on very high-strength steel, so you're normally using a 50 KSI material. We're actually making a steel casting with 180 KSI material, so it's got really limited ductility. But we're actually using some funky heat treatments now to try and get that grain refinement and get the performance up. So the mechanical properties that you need are available in steel castings. I don't know of any requirement that you might have that we wouldn't be able to make. We can make things higher than 180 yield, but then we begin to lose ductility and toughness. So we make the grinding media that people use. So we make castings with 500 or 700 Brinell, so they're up around 300 KSI. Ultimate, they don't have any yield. They just break.